good. So welcome to day 4 of the Nankai Dialogues. Our first speaker is Sung Soo Kim from UESTC in Chengdu, talking about BPS spectra. Thank you very much.
Thank you very much for the introduction, and also thank you, the organizers, for the invitations. So it's a great pleasure to talk about my recent work. I am Sung Soo Kim. Today I will talk about progresses on BPS spectra of 5D, 6D, n equal 1 supersymmetric field theories. Today I will not talk about 60 case, but nevertheless is extendable to 60. So mainly I will talk about 5D aspect. This work is based on various collaborations. The collaborators, let me introduce collaborators. The H.R. Kim, he's in postdoc, Korea, and Junho Kim is now a postdoc at IAS, and Min-Sung Kim is student at the postdoc, and Ki-Hong Lee is a postdoc at KAIST, and Kim Young Lee at KIAS, and Jae-Won Song at KAIST. So mainly I will talk about these two papers, but more focus on this bootstrapping BPS spectra of 5D and 6D field theories. So in this talk, so as I said, I will talk about n equal 1 5D field theories. Here, field theory, I mean the gauge theories as well as non-Lagrangian theory that doesn't have Lagrangian descriptions. So I'll talk about what I mean by this non-Lagrangian theory later. In particular, here I am interested in the how to compute the BPS spectrum of these theories. The BPS spectrum, I mean Nekrasov partition function, or sometimes known as the instanton partition function, or twisted partition function on alpha cross S1 and on the omega background. So this the subject has been extensively and studied over the past decades, and there has been many systematic way developed for computing this Nekrasov partition function. So some of which I highlighted in blue is ADHM and topological vertex and DIM algebra. ADHM is basically looking at the instanton quantum mechanics, and you can have the systematic way of computing a partition function for classical groups. Topological vertex is also using a type 2B or M theory description of theory. And then that relates to a topological string amplitude that gives rise to a topological vertex, and then it is equivalent to the Nekrasov partition function. DIM algebra is in the same category as a topological vertex. But there has been lots of computations and then further developments of these, and there was a very successful and very exciting. But on the other hand, although there is very successful in computing these partition functions, but there are still limitations. We know only some cases. I mean, although we have large classes, some cases still unknown, and there's a limitation of these systematic ways. For example, as I said, ADHM construction is limited to the classical gauge groups. So exceptional groups is still challenging. Although a noticeable one is the G2 case is very cleverly computed by embedding the by using the embedding of G2 to SU3. But other the exceptional gauge groups still is challenges. Not only that, if we have some matters in the higher dimensional representation, it's still difficult. And in 5D theory, we have a Chern-Simons level. As Chern-Simons level goes high, it's still difficult to obtain the partition function. From the topological vertex, a slightly different perspective. It is like you have a toric diagram or a five-brane web from the type 2B string theory. Then just like a Feynman diagrams, you have a Feynman diagram, you have a corresponding Feynman rule, and you compute the amplitude. You have a five-brane webs, and you can apply this topological vertex, and then a lot of the technique based on this topological vertex, you can compute this Nekrasov partition function. But although we know many five-brane webs, but still there are many five-brane webs for theories, such as exceptional theories, still is unknown. I don't know whether it's still possible or not. And also those with can be obtained by the orientifor is still challenging. So today I will discuss yet another powerful way. I think is very powerful. It is known as Nakajima, Yoshioka, the two mathematicians, Blow equations. So I will also discuss what is the Blow equation in more detail. So basically what I'm going to do is that I'm going to report that we devised a complete blower formulation that enables one to compute the BPS spectrum of any supersymmetric field theory that has UV completion, as in 5 dimensions or 6 dimensions. So the contents of my talk is, let me first review what I mean by the N=1 supersymmetric quantum field theories in 5 dimensions and its corresponding geometric engineering or M theory perspectives. And I will discuss what do I mean by the Blow equation and how to use it, and my main conjecture and why it is possible that the Blow equation enables us to compute all partition function or any partition function. And I also illustrated my conjecture with some simple examples, and I will conclude. So N=1 supersymmetric quantum field theories in 5 dimensions. It also applies to, let's say, KK theories, which is a 6th theory on a circle, keeping all KK modes. This N=1 supersymmetric theories, it has A supercharges. It also has a SU2R symmetry. The particle contents and the moduli space is as follows. We have a vector multiplet. Here, the Bojani content is described by the gauge field A mu and real scalar field. The total, the on-shell degree of freedom is 4, and there's a corresponding super partners, fermions. And the Coulomb branch is the branch where the gauge group is completely broken to the U1 to the rank of the gauge group. And it is parameterized by the expectation value in the vector multiplet is phi. And it, for short, probably I would denote by the CB, which is a Coulomb branch. It's one of the moduli space. Another one is we have hypermultiplet. It is complex Q scalars with the label of the SU2R symmetry. So there are 4 real degrees of freedom. And their expectation value parameterized the Higgs branch. So we have the 2 branches, Coulomb branches and Higgs branches. In 5 dimensions, there's a particular interesting the particle is the instanton, soliton, or instanton particles. It has a U1 conserved current, so it has U1 topological symmetries. Generically, this higher dimensional quantum field theory is non-renormalizable, but large class of theories shows that CFT there is a fixed point. More proper way of probably thinking about their fixed point or CFT is that, so if we think about the M theory, and the M theory putting in a Calabi of 3, and there is a 5D superconformal theories, and then returning on the deformation, and their arch flow describe the sort of the low energy 5D gauge series. So let me discuss more about this M theory compactification or geometric engineering. So M theory on a shrinkable Calabi-Yau-3 engineers 5D as superconformal theories. The shrinkable, is all holomorphic surfaces shrink to a point or non-compact two cycles. The singular limit of the Calabi-Yau is where the superconformal theories exist at the singularities. The building block of this Calabi-Yau-3 is a Hirschberg surfaces denoted by Fn or P2. The Fn is the degree of the surfaces, and P2 is local P2. So using this, we can glue these surfaces together, and then together with the blow up, we can realize the superconformal theories or 5D supersymmetric theories. As a simplistic example, I put it here. This local P2, their corresponding toric diagram or dual diagram is given like this. And the F1 is made out of this local P1 cross P1 is well-known example. And F1 is del plus 1, having this one. And F2 is like this, and etc., etc., etc. There's a corresponding 5D theories. The F1 and F0 all correspond to SU2. In fact, these correspond all up to SU2. There's some label known as a discrete theta parameter or discrete theta angle that has label 0, pi, 2 pi, etc., etc. Modulo 2 pi. So SU2 is basically equivalent to SU2 with 2 pi, and SU2 has a distinct feature. I'll talk about this one more later. And the from here, you see that these theories has a gauge theory description as SU2, but this F2, which is possible, but this does not have the gauge theory description. It is sometimes known as called E0 theories. I can also relate this to theory. This F1 is geometrically, it is a DP1 or the 1-point blob of the P2. So from blowing down this, I can get to this P2. Or from the SU2 pi theory point of view, we have some instantonic hypermultiplet. I can integrate out, and then I can get the this non-Lagrangian series. And the other, the higher rank theories can be obtained by gluing with certain conditions, and I can get the various series. For example, SU3 with a 0 and SU3 with 1. This label is different from these labels. These are discrete theta angle. This discrete theta angle only exists for SPN theories in 5 dimensions. So SU2 is SP1, so they have a discrete theta. But on the other hand, this SU3 series has a Chern-Simons level. These are actually Chern-Simons levels that I'm talking here. This is labeled. So you can imagine that other Chern-Simons theories with other Chern-Simons level can be also obtained by increasing, by replacing with a different Hirschberg surfaces. There has been lots of discussions and also works in classification and geometrically, and there was very successful. And as you can see, that there are many papers, and this is a very hot field. And today I will talk about more about this gauge series description and then the partition function with a known classification for rank 1 and rank 2 theories. So as we discussed geometric engineering, so let me also make some comments on their correspondence. So basically, if we have a superconformal theories, and from the gauge theory side, then we have a corresponding Calabi-Yau, and then Coulomb branch is correspond to the Kähler cones. W bosons, or it basically tells you how many W bosons basically tells you how many compact force cycles, and the flavors or is connected to the non-compact force cycles. And the BPS state is coming from the M2 brane wrapping compact 2 cycles, and their masses or BPS masses of these BPS state, basically they are the volumes of these 2 cycles where the M2 brane is wrapping. So, and the BPS charges are the intersection number between 2 cycles and 4 cycles. So partition function that I am interested in is, in fact, is Witten index counting this BPS state, which are annihilated by the supercharged Q and Q dagger. So here this Z is, I'm going to denote that this is a BPS partition function or Witten index. It's formally defined as a trace over the these operators. F is the fermionic number, and these are 2 supercharges, and these are the combination of the charge, the operators that is commuting with this particular combination. J1 is the SR4. We have the 2 rotation generator, J1 and J2, and JR is SU2, and this phi are the gauge cartons, and this H is associated with the flavors. So here the M is mass of the hypermultiplets, and this phi is Coulomb branch parameter, and the epsilon 1, epsilon 2 are the two omega deformation parameters. So these are the partition function that I'm interested in. And the property of this BPS partition function is that it has a factorized in the one perturbative part and instanton part. And this perturbative part, we can also have a classical part and the one loop part. These are basically it tells you this is coming from the vector multiplet, and this is coming from the hypermultiplet, and this e to the epsilon. I mean the curly e is an important thing. I will discuss about more later. So regarding the notation, I'm going to use a P1 and P2 rather than epsilon and epsilon 2, which is an exponentiated value. And the R I denote as a positive root. Sometimes I use R, which is an older root. And this WF is the weight where the hypermultiplet belongs to. And this F is the number of the hypermultiplets. And PE is a notation that keep track of the like multi-particles, and is defined as exponentiated with all this infinite sum. So okay, now let me discuss the below equation. So the partition function I am interested in this is a partition function on the omega deformation, and omega deformed R4 times S1 or C2 times S1. Below equation is a functional equation identifying 2 partition functions on different background. So suppose that I have this R4. Okay, here. So here I can I have a partition function. Okay, define this R4. here, let me just skip that there's S1. Oops. So, and then blow up means that the origin I replace I replace the origin by the S2 or P1. And then the geometry is now changes. It's below one geometry of C2. And there we have two fixed points, which is located in the north pole and south pole of S2. So, and then computing the partition function in this background, I have the product of the partition function on this north pole and south pole, and basically the partition function is two partition function, and here S2 I can also turn on the fluxes, and summing of all the fluxes, I will have the partition function on this geometry. But we can also think about the blow down precision, where the S2 is smoothly blowing down and going back to the original and this geometry. So therefore, the summing of all these partition function of the north pole and south pole should be equal to the original partition function. And this is a basic idea of the blow equation. This blow equation, let me put it in a more better systematic, a little bit more better systematic way. So here is the origin of C2 with the coordinate in Z1 and Z2. And I blow up and I insert the P1, and there's north pole and south pole. And the blow equation is the summing of all possible fluxes defined on the this north pole and south pole, with the introduction of this particular lambda. The important point is that this lambda doesn't depend on the Coulomb branch parameters, and then these defines the blow equation. So this blow equation is, as you can see, is not a linear, is a nonlinear equation. So it is it gives rise to recursion relation among these partition functions. Here I denote by n and s is the partition function on north pole and south pole, with a local coordinate is shifted due to these fluxes with the epsilon parameters, and then given as this way. So it's a terminology is that if this lambda is not of course it's not a function of phi, but if it is not 0, then it's called unity equation. If it's 0, and it is called vanishing equation. So here I introduce fluxes N and B. So N is magnetic fluxes associated with the gauge symmetry, and B is the magnetic fluxes on P1 with the global symmetries. Okay. So there has been various studies and generalization, starting from the original work of Nakajima and Yoshioka in the 40s. And then soon after, it was generalized to the 5D SUN. And there has been lots of the developments, exceptional gauge groups, and also elliptic blow equation, and even the surface defect. This shows that there has been a lot of interest, and it is a good way of the computing partition functions. But in fact, there was some was not complete in the sense that there are still many cases that we didn't know how to solve, how to obtain the partition function, even though we use the blow equation. And today I will talk about it is still we can still use this blow equation and compute the all the partition functions. So here's my main conjecture. So the partition function that I'm going to compute as basically the form. So it has some classical part, and also it has a Gopakma buffer form. Okay, this is like an index part, and this is a classical part. So using this, the property, so my main claim is that if we know two inputs, which I call the effective prepotentials and consistent magnetic fluxes, provided that these two inputs, one can always use this Blow equation and to compute or determine this partition functions. So what are these effective prepotentials and the consistent magnetic fluxes? Let me discuss about what it is. So effective prepotential, I'm sorry, by the way, how much time do I have?
You've got almost 10 minutes still.
I have 10 minutes?
Yeah.
Wow. Okay. So okay, let me hurry up. Then in 5-dimension, in 5 field theories, so effective action consists of the 3 different Chern-Simons terms, and cubic Chern-Simons term, and mixed gauge gravitational Chern-Simons term, and mixed gauge and SU2 Chern-Simons term. So detail maybe is not very important, but these all give rise to can be used to define the effective prepotential. Effective prepotential, this curly E, it has F, which is known as also cubic prepotential, or sometimes known as the interligator Morrison-Seiberg prepotential. And basically, it has a form of the instanton or gauge coupling squared, and also, and then this is a Killing form of the gauge group. And this one has to do with the Chern-Simons terms, and it has one new part, which is coming from the vector multiplet and hypermultiplet. Basically, this term can be determined if you know the gauge theory. The gauge theory that you want to compute is you have in mind, then this cubic potential you can just compute. And then the other two terms is coming from the mixed Chern-Simons term with a gauge and gravitational Chern-Simons and gauge SU2R symmetry. They have the form, can also be determined if we know the theory. If we have the gauge theory description, these can also be simply obtained. In geometry, we can also compute these Chern-Simons terms, as this cubic Chern-Simons term is coming from the triple intersection number, and the coefficients here and here from the geometry is just the intersection of this C2, which is second Chern classes of the Calabi-Yau, and then their intersection give rise to this. So as we know, the old Hartree-Wolff surface is this is if you know the geometric description, it can be computed, and these coefficients with the mixed cubic with the R symmetry, it is always true if we use thinking basis. For example, if pure SU2, so it comes from this gauge coupling, and there's a cube is quadratic, and SU2 has no flavor and no Chern-Simons. The other two terms are simply 0, and this is coming from the vector multiplets. And you can also compute using this information, and this is what it is. On the other hand, this local P2, which doesn't have the Lagrange description, but we do have the geometric description as a local P2, which has a triple intersection number 9. And as this is a -6, we can get this. And simply, these are two theories. Here, the message is that if we know the gauge theory description or geometric description, we can always compute these effective prepotentials. So here I put the two geometry which is associated with the pure SU2. As I said, there's a discrete theta parameter pi 0 and pi. Their geometric description is different, F0 and F1. So, but this effective prepotential, they are not in this. They are not distinguishable. But these two geometry or these two theories is distinguishes. In fact, the Blow equation distinguishes is due to the fluxes that can be turned on both cases are different. Okay, let me talk about what are these two cases. So the magnetic flux is that I turn on N and B, which is associated with gauge symmetry and the global symmetry, cannot be arbitrary. It satisfies some quantization conditions. Suppose that I have the M2 brane wrapping 2 cycles, C, which is BPS state, of the charge of the Lorentz charge or Lorentz spin, JL and JR, that couples to the flux F. This F and C, their quantization is integer or half integer when the C square, which is self-intersection number, is even or odd. Well, equivalently, if we know the spin, depending on this JL plus JR, and twice of them is even or odd, we can have the same equivalent quantization conditions. For example, let me give a very simple example, which is a W boson, whose spin is JL is 0 and JR is 1/2. Plugging this spin, I see that it is 1. And therefore, it is odd. So we have turned on the integral or integer fluxes. On the other hand, we have hypermultiplet. Hypermultiplet has charge spin 0, 0. So obviously, this is even. The condition is half integers. The fluxes that we turn on is half integers. From the geometry point of view, this W boson is associated with these fibers or fiber classes, and their volume is basically the parameterized the charge of this. But this geometry is basically the self-intersection number is 0. So as this is a 0, so we get the integer fluxes. So here in the fiber class is the same, so we will have for the gauge symmetry, we still have the integer fluxes. So for these different theories, for the gauge symmetry, we have integer fluxes. On the other hand, this part, which is has to do with the base, this base fluxes has still the self-intersection 0. So therefore, we have integer fluxes. Well, that is obvious because the F0 is nothing but P1 cross P1. So we should have the W bosons. On the other hand, this F1, the base classes has the -1 curve, which is a hypermultiplet, and therefore we'll have the half integer fluxes. And these two are the basically possible quantization conditions. But although, I mean, we already have some conditions, we have to also think about one more important thing, which is in the Coulomb branch, the theory to be consistently well defined. We have to think about the chamber where all the masses of the BPS particle should be non-negative. This actually gives rise to further restrictions on the background fluxes. And for these F0 cases, we have only available one is 0 and ±1, ±2. And these F1 cases, we have ±1/2 and ±3/2. I think I do not have enough time, so let me speed up a little bit. And so with this input, I have this effective prepotential can be easily obtained, and magnetic flux. So we can have some condensation condition and can get the I call them consistent magnetic fluxes, and then with these conditions, two inputs, I can recast the Blow equation in this way, where I put the effective prepotential and sum them together as a V, and these are the North Pole and South Pole. And as we have three unknowns, the original one and the one in the North Pole, the one in the South Pole, we have three unknowns, so if we provide the three different set of the magnetic fluxes, then we can get the three equation, and we have three unknown. Therefore, we can obtain this partition function without much problem at the order. So this is a case, but I mean, it will be good if we every time we can find three different sets of the magnetic fluxes, but it's not always the case, and this is an important part of my talk. So the basic strategy is that if we do not have the magnetic fluxes, sets of magnetic fluxes less than three. I mean, I'm sorry, what am I saying? If we have only one or two set of the magnetic fluxes, then I'm claiming that we can still obtain the partition function. Here's how. So we first expand the partition function in terms of Kähler parameters. Okay, and then try to solve this Blow equation order by orders in the Kähler parameters. And there, as the partition function is in the form of Doppak-Mel alpha, and these here's maybe I skipped. These are the partition function, where the m is the two cycles, the volume of two cycles, and then these are the degrees of two cycles, or how many times M2 brain wrapping. And these are the SU2 part, and then this is SU2 characters. The important thing is that here we have n, which is a multiplicity of the state with a spin j and jr. So basically, I mean, if we know, I think what is important is fixing this multiplicity is basically the crucial job. So the point is that by expanding in terms of Kähler parameter and restricting ourselves to the order by order, we are going to determine this D. So, but it's not always straightforward. Some cases we can determine, some cases still remains undetermined. In this case, we carry out this undetermined multiplicity to the using them as another input to the higher orders of the Blow equation in the Kähler parameters. And as this is a Blow equation is a recursive relation, we are using the iterative way to fix these multiplicities. Okay, let me give you, I don't know, probably I'm running out of time. Do I have a,
yeah, we're running a bit short of time for questions, but you have a minute or something if you want to take that.
Okay, so let me then briefly go over some of them. So SU2 case 0 pi, we have a magnetic flux is more than 3, so it can be easily computed. So the partition function, that the solution is given like this. So, but here's a thing that I am can require some minutes. Suppose that I only know, I mean, although I know the answer, this is an illustration when we only know one the magnetic fluxes. For example, suppose I only know that the background magnetic flux is 0, and I recasted the flow equation where the Kähler parameter has a base and then fibers, and here I expand only looking at the instanton part of the first instant, I mean the one instanton part, and I further expand in terms of the this higher powers of the this volume of the fibers, and then this. So, and then I looking at the order by orders of these T2, whether, for example, this is one instanton. Here this is D1, and D2 is the part that I'm going to looking at, and I'm looking at the orders, and I see that only these 3 terms are necessary, and then but in this computation, these terms with a spin of 0.5, which is this W boson part, is not fixed, so this combination is 0. But other terms can be fixed, so I put this condition to the high orders, and I repeat the same thing at the given orders of the D2 or the 1, 2, 3, and in fact I can determine it. And then it turns out that it is 0 for D2 equals 0, otherwise 0. So this is in fact the same as the previous cases. It's just that you expand these, and then you get the multiplicity where everything is 1. So I can have other the cases. As I'm running out of time, let me wrap up. We can actually go over the KK theories as well, but let me conclude. So I'm trying to convey some idea of the systematic bootstrap way that allows us to compute the any partition functions for n equal 1 gauge theory using the Nakajima-Yoshioka's flow equation. For those that has the gauge series description or geometric description, there's 2 input that I impose. The effective potential can be easily obtained using these descriptions, and the magnetic flux. And then iterative way, we can compute the over the partition function. Okay, so due to time, let me stop here.
Thank you very much, Professor Kim, for a very interesting talk.